Our goal today is to define a new metric space by defining a metric on the set of linear maps from Rn to Rm. So this is going to be going a little bit into Rooted in Chapter 9, but we won't actually define derivatives. We'll leave that into the study of derivatives for 118c. For 118b, this is just going to be an example of a metric space. All right, so notation. If I write L x, y, where x and y are vector spaces, then let's make that stand for the set of linear maps from x to y. And for us here, we're just going to be concerned with this special case, where we're putting the vector spaces Rn and Rm here. So L, Rn, Rm stands for the set of linear maps Rn to Rm, which you could also write like this, the set of A mapping Rn to Rm such that A is linear. Now, my goal is to define a metric on this set so that this becomes the underlying set of a metric space. But we'll do that by defining a norm. So first let's notice some things. If I take A, a linear map from Rn to Rm, then A is continuous. That's something you showed on a previous homework problem, that A is continuous. So there are a number of ways you can show that. There's a post on Campus Wire discussing different ways of showing that. So this is continuous. That means if I take the image of a compact set, I get a compact set. So here's the compact set I want to focus on. So the kinds of sets that I can take images of are subsets of Rn, n-dimensional Euclidean space. And if I take the unit ball in Rn and take the closure of that, then that, just to be clear about what that closure is, that's the set of vectors in Rn. Let me specify that this is an Rn type of unit ball. It's a set of vectors with norm less than or equal to 1. Okay, so this is something you could prove, that the closure of the unit ball consists of these points. And this is compact. So here I'm referencing the Heine-Borel theorem. This is a closed set because it's the closure of something, and it's a bounded set. Clearly it's bounded, it's inside the ball of radius 2 at the origin. So it's compact. Therefore, if I take its image under A, then that's compact. So then this is compact. And actually, the norm function, so there's a function that takes norms of vectors in Rm. That function is continuous also. So A is continuous, but also this norm function is continuous. And that's pretty easy to prove. I don't know if we've ever had that as a homework problem, but if not, it will be one. So the image under the norm function of this set is also a compact subset of R. So allow me to express the image under the norm function of this set by just writing bars around this set. So this is a subset of R, which is compact. Okay, a compact subset of R, a non-empty compact subset of R. This is definitely non-empty because I'm taking the image of a non-empty set. We'll always have a max. So the max of this thing, this set, exists. And we define that to be the norm of A. So this is a new thing. The norm of a matrix, or a linear map. It could be represented by a matrix. So the norm of a linear map is defined like this. Look at, so here's another way of writing it. Take the max of this set. So I'm just going to describe the image in another way. look at A applied to X for all the X in Rn such that X is no more than 1 away from the origin. And look at how far AX is away from the origin, and then take the maximum of those. So that, you can think of this as a way to measure kind of the size or the magnitude of a linear map. All right, so you might have noticed that I'm using single bars for norms here, and here, and here, and here, and I often used to use double bars for these. It's really a matter of convention when you're working with a norm, whether you use single bars or double bars. Typically, I will just use double bars to distinguish one norm from another. And what I had been doing was I was using double bars to point out to you that we're using Euclidean norm in higher dimensions as opposed to the basic absolute value. Now the distinction I want to make is between Euclidean norm in any dimension, so I'll use single bars for all of the Euclidean norms in Euclidean space, and this new thing, which is the norm of a linear map. So I've been using the word norm, and we have not really defined that in this course, but so far at least what you're seeing is that we've defined some operation that I'm now indicating using double bars that can be applied to linear maps from Rn to Rm and gives you real numbers. It gives you, it's defined like this, so it gives you the maximum of these values, of these real numbers. Okay, so the properties that we're about to look at for this thing are the things that make it a norm. The first one, maybe, is it's at least greater than or equal to 0. So this takes values not in R, not just in R, but further, it's taking values here, non-negative. Okay, that's clear because it's the maximum of a set of non-negative real numbers. Since it's the maximum and not just the supremum, it's actually very easy to think through things like this. It is one of them. So the norm of A is A applied to some particular vector, one of the vectors in the closed unit ball. So it's definitely something non-negative. But more than just being non-negative, it's positive definite. So what that means is if the norm of A is 0, then A is the 0 linear map. Okay, so now it's worth noticing, so when I say 0 linear map, it's worth taking a moment to appreciate that the set of linear maps from Rn to Rm is a vector space. It's a vector space with respect to pointwise addition and pointwise scaling. So this is a real vector space. So when I say 0 here, I mean the 0 vector. In general, when one talks about norms, one talks about norms on vector spaces. So what we're doing is equipping this vector space with a norm. Okay, so this is the first thing that makes it a norm, is that it only takes the values, it's non-negative, and it's only actually 0 when the thing that you're taking the norm of is 0. All right, I guess this one is pretty obvious, right? Like, if the maximum of all of these is 0, all of these are non-negative, so then all of these must be 0. So then A vanishes on, A vanishes on everything in the unit ball. So A definitely vanishes on a basis. So A has to be the 0 linear map. All right. The next property is if you scale A, so thinking of A as a vector, but it's a linear map from Rn to Rm, if you pointwise scale it, then that should be this. And finally, the triangle inequality. So if you take two linear maps and you pointwise add them and then you take the norm, then that's bounded above by Okay, so this is all item 9.7 in Rudin. So you can read through the justification of these if you want, but let's do this one together. So let's prove the triangle inequality. So let A and B be linear maps from Rn to Rn. Then if we want to prove, so want I want to prove that this, which is a certain max, is bounded above by this. So I want to prove that a certain maximum of a certain set is bounded above by this. I can do that by showing that this is an upper bound for that set. So I want to show that this is an upper bound for what set? The set whose max I'm taking to define this thing. So for the set of A plus B applied to X, running over X in the unit ball. Okay, so to verify that it's an upper bound, fix X in the unit ball. So let X be in Rn such that the norm of X, so here I've been using single bars, such that the norm of X is less than or equal to 1. Then, actually, the set whose max I'm taking is not this set. This is a set of vectors in Rm. The set whose max I'm taking is this set, the set of their lengths for their norms. Okay, so I'm trying to show that this real number is an upper bound for this set of real numbers. So then, this arbitrary element of the set that I'm trying to bound above is, well, first of all, it's this. By the definition of the pointwise addition. That's how the vector space structure on this set is defined. And by the triangle inequality, so I'm proving the triangle inequality for these double bars, but we already have the triangle inequality for the basic Euclidean norm in Rm, so I can use that. By that triangle inequality I have this. And then, since X is in the unit ball, the norm of Ax is bounded above by the maximum of the norm of the Ax for all X's in the unit ball. So that's this. And similarly, this is bounded above by the norm of B, which is the maximum of all of these running over all X in the unit ball. All right, and that's it. We're done proving the triangle inequality because we have shown that this real number here, this constant independent of X, this is an upper bound for all of these. So it's greater than or equal to the max.